All right, so let's continue where we left off in the previous class. I was talking about this algorithm called accelerated gradient descent. So it's a mechanism of improving the rate of convergence of standard gradient descent. We've seen a total of three classes of algorithms. One was the standard gradient descent or vanilla gradient descent. The second was the class of mirror descent algorithms. And the third is this accelerated gradient descent. And one interpretation of accelerated gradient descent was that you have two sets of iterations that are kind of running in parallel. One, a set of gradient descent. So the xt essentially follows a gradient descent algorithm. And you have another sequence zt, which follows a mirror descent type of algorithm. Right? And in general, it's difficult to give the intuition behind accelerated gradient descent. But nevertheless we'll see the behavior of or try to interpret the behavior of accelerated gradient descent in today's class. Okay, and the main advantage of using accelerated gradient descent or an acceleration mechanism is that it can vastly improve the rate of convergence. So one can show that under the same set of assumptions that we've been following so far, the number of steps required to get epsilon close to the minimum is something that depends on 1 over square root of epsilon. This is compared to gradient descent, which requires order 1 over epsilon number of iterations to get epsilon close to the minimum. Right? And the high level idea was the following. The intuition behind the design of accelerated gradient descent is that you want to obtain a sequence. In each step, you're constructing not just a sequence of xt's, but also a sequence of phi t's. So it's a sequence of functions which try to approximate f of t better and better in some sense. So what we're claiming is that what the accelerated gradient descent algorithm does is it constructs a sequence of phi t's which satisfy the following property. That is, phi t of x is less than or equal to some convex combination of f of x and phi 0 of x, some scaled version of phi 0 of x for all x, and f of xt is less than or equal to phi t of x for all x. So it's kind of phi t of x is sandwiched above and below by, from above it's less than or equal to some convex combination of f of x and phi 0 of x, and it's bounded from below by f of xt. And note that lambda t is a sequence that tends to 0 as t tends to infinity. So as t becomes larger and larger, phi t of x is upper bounded by f of x for all x. So it's a strict lower bound for f of x everywhere. And it is also lower bounded by f of xt. Right. So first I'd like to give, we'll just do a very high level analysis of the convergence rate of this particular algorithm to see why, suppose that we can actually guarantee these conditions. Phi t of x is bounded from above and below by these functions, then in fact you get this promised rate of convergence. All right. So again, let's recall the assumptions that we've made on the problem. So the goal is to perform unconstrained minimization of some convex function f of x, right? Unconstrained minimization. We assume that we're not too far away from the actual global minimum. So x0 minus x star is the L2 norm is at most some quantity d, and the gradient of f is sufficiently smooth in the sense that gradient f of x minus gradient f of x prime is upper bounded by some constant L times x norm of x minus x prime, and this holds true for all x and x prime. Okay, so these are standard assumptions that we make. Here's an exercise. So this second condition, that the gradient is sufficiently smooth, also tells you something more about the function itself. So recall that since f is convex, it can be lower bounded by the first order Taylor series expansion, or in other words, it's lower bounded by the tangent plane passing through any particular x. Right, so f of x for any x is lower bounded by f of, let's say, x bar plus gradient f of x bar transpose x minus x bar. This holds true for all x bar because f is convex. That is straightforward. But the second property, let me call this property 1. Let me call this second property. The second property implies that this f of x is also less than or equal to f of x bar plus gradient f of x bar transpose x minus x bar plus L by 2 times the 2 norm of x minus x bar the whole square. Alright, so f of x is in fact sandwiched above and below. It's sandwiched from below by the first order Taylor series expansion, but it's also sandwiched from above by a second order by a quadratic term, right? So this in fact says that f is L strongly convex. Right, so I'll leave it as an exercise to prove this second part, that f of x is upper bounded by this quantity if property 2 holds. Okay. Alright, so now going to the analysis of accelerated gradient descent, we want to show that we get this 1 over square root of epsilon rate of convergence, right? Or in other words, epsilon is bounded by some 1 over t square, right? So let's assume that we can in fact construct a sequence of lambda t's, phi t's and x t's with the following properties. That is, this phi t of x is sandwiched from above and below as I discussed previously, and lambda t decays at sort of a quadratic rate. So it is upper bounded by some constant divided by t square. Okay, and I'll make another assumption that the Bregman divergence between x0 and x star is also bounded from above by d square. Okay, remember that this is a broad class of algorithms. I can choose my function r as I want. For example, if I chose, say, dr of x prime to be, let's say, norm x minus x prime the whole square. I think I should take half x minus x prime the whole square, just x minus x prime the whole square. Then this is already guaranteed by this particular statement over here, right? So that's nothing new, but in addition to this, I also want, irrespective of which r I choose, I want this particular guarantee. If not, I can just take d square to be the larger of x star minus x naught the whole square and dr of x naught comma x star. I can always do that. Okay, so let's suppose that we have these assumptions. We are able to construct, and in fact, it's more involved to show that what accelerated gradient descent does is that it produces this set of functions phi t, and lambda t also satisfies this. So I won't get into the proof of those, but let's assume that this holds. Okay, so in that case, let's look at f of xt. My goal will be to upper bound this f of xt by f of x star plus some term that depends on t, l, d, and so on. Okay, so first what I have is f of xt is less than or equal to phi t of x. That's already guaranteed to me, and this holds true for all x. This is less than or equal to phi t of x for all x, and in particular it is less than or equal to phi t of x star. This follows from assumption 2, right? But in the last class I also told you how you choose phi t of x. So you choose phi t of x in this particular manner. Okay. Correct. So phi t of x is less than or equal to 1 minus lambda t f of x plus lambda t times f of x naught. In fact, I'll do it in two steps. So have phi t of x is less than or equal to, just do that. So this is less than or equal to 1 minus lambda t f of x star. I'm using property 1 plus lambda t L by 2 phi naught of x phi naught of x star. Okay, but what is phi naught of x? Right, so phi naught of x is f of x naught plus something times dr of x comma x naught. So this is 1 minus lambda t f of x star plus lambda t times L by 2 times f of x naught plus some constant dr of x comma x naught. So that's dr of x star x naught. Let me change this. Okay, so this is 1 minus lambda t. Let me sort of collect the terms involving x naught, x star, so this is f of x star minus lambda t times f of x star plus
So the first one in equality and not in the equality because the
which one?
assumption one is that the first time you put the equal sign, your assumption one is less than equal.
I'm sorry, this is an
That is
inequality.
fine.
This is an inequality.
Those two steps are fine, but the
Okay.
next one.
Because I've chosen phi naught of x star, so phi naught of x is chosen to be f of x naught plus this particular quantity.
So it's not assumption.
It's not assumption.
No.
So second step is assumption one. But now I think I should have chosen this a little carefully. Okay, so let me change this a little bit. Sorry for the mix up. So phi t of x, let's take this to be just a convex combination of f of x and phi 0 of x. Right, so there is no L by 2 over here. There is no L by 2 over here. So I get this minus eta times dr of x star x0. Okay, fine. So now I want to express this. So I have f of x star minus something, correct? In fact, let me express this as plus f of x naught minus f of x star plus this. Okay, so I want to express this as f of x star plus some quantity, and I want to bound this particular quantity in terms of the parameters that I already have. Okay. So I want to bound f of x naught minus f of x star. I know that this quantity is already upper bounded by d square because that's my assumption. That was assumption 4. This is assumption 1. By assumption 4, I know how to bound this particular quantity, but now I need to bound this particular quantity. And what can I use? I want to make use of this particular fact, right? That f of x is less than or equal to what, or f of x naught is less than or equal to f of x star plus gradient of f at x star times x star minus x naught. Right, so this is less than or equal to f of x star plus lambda t. So f of x naught is less than or equal to f of x star plus gradient of f evaluated at x star transpose x naught minus x star plus L by 2 times L2 norm square of x naught minus x star square. Right? And this basically follows from this particular property, the L-Lipschitz property of f. and I have this eta times dr of x star x naught. Okay, what can I say about this particular term here? Why? Well, in a way you're right, but you can say something stronger. What is x star? Okay, so what is gradient of f of x star? Should be equal to 0, right? Because we're doing unconstrained minimization. The unconstrained minimum means that the gradient of f of x star should be equal to 0. So this whole first quantity is equal to 0. This is 0. Right, so this is f of x star plus lambda t times L by 2 norm of x0 minus x star square plus some constant times dr of x star x0. Now from assumption 3 and 4, or sorry, from assumption 4, this quantity is less than or equal to d square. This quantity is also less than or equal to d square because we've assumed that the initial point is not too far away from the global minimum or global minimizer. So this is less than or equal to f of x star plus lambda t times L d square divided by 2 plus eta times d square. Right? Now eta is kind of a free parameter that I have not chosen yet. Right? You can think of it as like a hyperparameter, if you will. So if I chose eta to be equal to L by 2, then this quantity is basically equal to f of x star plus lambda t times L d square. Correct? But what do I know about lambda t? It's less than or equal to some constant divided by t square. So this is less than or equal to f of x star plus some constant times LD square divided by t square, or f of xt minus f of x star is less than or equal to some constant times LD square divided by t square. So if I want this quantity to be at most epsilon, right, then the number of steps that I require is less than or equal to some constant times LD square by epsilon, or t square should be less than or equal to some constant times LD square divided by epsilon, or the number of steps required is at most square root of this constant times LD square divided by epsilon. Question? Now there are many different. Any questions regarding this particular approach?
So choosing L2 square now.
Correct.
L2 now square. I had chosen a higher power. Would I have gotten a faster convergence?
Which one? Sorry.
Like where you stipulate that condition, right?
You mean lambda t?
No, the stronger version of that gradient inequality.
Oh, you mean
Yeah.
you mean to say this particular constraint or
No,
this particular constraint? The second one.
Two inquiries, the homework problem.
Oh, this.
Yeah.
This doesn't really give you anything much, right? I mean, this, what you can improve is maybe this particular constant. So,
What I meant is instead of just square of L2 now, if I put like higher order terms, that's not going to improve it.
that doesn't improve anything. But here is something that will improve the rate of convergence. So, suppose that the function is some sigma strongly convex for sigma which is strictly less than L, right? That is, f of x is less than or equal to f of x bar plus gradient f of x bar transpose x minus x bar plus sigma by 2 times norm of x minus x bar the whole square. Suppose you know this for some sigma that is strictly less than L. Okay, so
it's a constant.
which one?
That
Sigma is a constant. Sigma is a constant. So it's a property purely of the function f. Right? Sigma strongly convex with a parameter sigma less than L. So remember that L is what you get from gradient f of x minus gradient f of x bar less than or equal to L times x minus x bar. Right? This holds true for all x bar. Which one? F of x is, no, that's not the definition of strong convexity. So f of x is always is lower bounded by f of x bar plus, like, without this term. So forget about strong convexity. Just convexity implies that f of x is greater than or equal to f of x bar plus gradient f of x bar times x minus x bar.
So I think what you asked is the very first one, should it be a greater than equal to? That's what you are saying.
Yeah. I know that. But convexity ensures that this is greater than or equal to this.
So in this screen, you are assuming f is convex?
I'm assuming that f is convex. Oh, I'm sorry. You're right. This should have been. So it's low bounded by quadratic and not just linear. Right. Right. Okay. So suppose that this is also strongly convex, sigma strongly convex for some sigma which is strictly less than L. Okay. So remember that this is also upper bounded by this particular quantity, f of x bar plus this particular quantity. That purely comes from say that. Let's ignore this for now, but this purely comes from the fact that the gradient is L Lipschitz continuous. Okay, so if this is true, that it is sigma strongly convex for some sigma which is strictly less than L, then the rate of convergence, you can show that the number of steps required to get epsilon close is some constant. I don't remember the exact parameters, the dependence on L, D and sigma, but the dependence on epsilon is log 1 over epsilon, not even 1 over square root of epsilon. Right? So in other words, epsilon is something or something times e to the power of some constant times or minus constant times t. So here, with just these assumptions, what we got was a quadratic rate of convergence. Right? The error or the loss is upper bounded by something divided by t square, where t is the number of iterations for which you have run. But in fact, if you have strong convexity, then you can get an even faster rate of convergence, and that's an exponential rate of convergence. Right? So in fact, the original version of accelerated gradient descent, which was proposed way back in the 80s, was for strongly convex functions. Right? So if you take, let me assume that this alpha is L divided by sigma, which is greater than 1, then the original version the iterations look something like this. So you run the following. So you take yt plus 1 to be equal to xt minus gradient of f evaluated at xt, and xt plus 1 is a linear combination of yt plus 1 and yt. So you take this to be 1 plus square root alpha minus 1 divided by square root alpha plus 1 times yt plus 1 minus square root alpha minus 1 divided by square root alpha plus 1 times yt. Or so this basically gives you another interpretation of the accelerated gradient descent mechanism. So this, you can write this as yt plus 1. Let me substitute yt plus 1 into this particular quantity. This is 1 plus, let me call this whole thing beta, right? So 1 plus beta times xt minus gradient f of xt minus beta times Let's just leave this at as yt. This is equal to xt minus gradient f of xt plus beta times something, right? Some function, let's call this g, that depends on xt and also depends on xt minus 1. Okay, and this beta is something that is so this beta is something that is less than 1. So this is like gradient descent, but instead of taking the full step along the gradient, you have this additional term which is like a damping term that you add, right? Damping is not strictly the right word to use, as we'll see a little bit later, but basically what accelerated gradient descent does is you take larger steps in gradient descent, but eventually you keep damping it in a way that you take larger steps but in some sense converge faster. But what is to be kept in mind is that this is in some sense the direction along which you take one step, right? You take xt plus 1 is xt minus something times a direction, and this direction is not along the direction of the negative gradient. So you are not guaranteed that in every step the objective function is going to decrease. It is possible that in some steps the objective function will increase, but overall you will have the objective function will decrease. The overall trend is that the objective function keeps decreasing, but from the current iteration to the next iteration you're not guaranteed that the objective function will decrease, right? So to see the behavior, let's take a concrete example and implement gradient descent and accelerated gradient descent. Okay? So let's take, say, the least squares problem. So the objective function is minimize ax minus b L2 norm square, right? Where A is a full rank tall matrix. Okay, so in this case, let's sort of write down everything. Let me pick a random matrix A. Let's take Mn to be, let's take 5 by 2. So A is a random m by n matrix, and B is a random matrix of size m. I get something. It doesn't matter what it is. So now let's find the least square solution for this particular problem. We can evaluate it analytically. What will it be equal to? Yes. Yeah. A transpose A, code inverse, times A transpose times B. right? So I get some particular x, right? Okay, let me try to approach this using gradient descent. So first, let me write some helper functions to compute the value of the function, that's the 0th order oracle, and also write a function to compute the gradient, which is the first order oracle. So I want to compute f. My f is L2 norm of, and so the parameters are a and b and x. So this is just norm of a x minus b L2 norm square, right? Yeah, I also need to compute the gradient, the first order oracle. What is the gradient going to be equal to? Yeah, so f of x is square. Yeah, what is it equal to?
A transpose A.
A transpose A x minus A transpose B. Are you sure there's no constant that is missing?
L2
So you can evaluate it, right? Yep, so it's 2 times A transpose AX minus 2 A transpose B. So this is 2 times transpose AX minus. Okay, fine. So now let me run gradient descent and see what I get, like standard vanilla gradient descent. I'll pass as parameters a, b, the actual solution, just to compare at every step how far away my solution is to the actual solution, and the total number of iterations. And I'll also choose different step sizes to see how gradient descent behaves with different kinds of step sizes. Right, so first I'll begin with, I'll also pass an initial point x0, just to make sure that for all algorithms I'm using the same initial point, because it may be possible that if I rerun with a different initial point, the number of iterations I require is going to be different. Right, so let's start with some particular initial point. So let's take x to be equal to now I need to choose the step size. I'll also find the optimal squared error. So this is nothing but compute f of abxls. This is the optimal error that I can possibly hope for, and at every stage I'll try to find out how far away am I from the optimal error. Total number of iterations. So I'll choose the step size in three different ways. One is I'll choose a constant step size. I'll choose a sort of 1 over t kind of step size, and also a 1 over square root of t kind of a step size. Is 0. So if my choice is 0, then I'll choose step size to be equal to let's say 0.01, or I'll choose this to be 0.01 divided by say t plus 1. Or square root of t plus 1. Okay, one of these three different step sizes. So x, and how do I, what is a gradient descent step? You just take x minus step size times gradient at x. Okay, just that, nothing else. So this is the main gradient descent step. Now at every stage I also want to see how far away am I from the optimum. Right, so I'll take loss to be equal to the error at x minus the objective function at the current time step minus the best possible, the lowest possible error that I can achieve. Okay. And for now, I'll just, once all of this is done, I just output the loss. Okay. Any questions? That's all right. So let's plot this for uh, some arbitrary x naught. Okay. So I'll pick a random initial point and it will be loss of t. Which one? Correct. That's right. Hmm. So if so for different choices of the step size, let me just find this out. So loss is equal to gradient descent a b x naught x ls. Let me fix the number of iterations to be 100. And step choice is this. And I want to plot this loss gradient descent yes. This is too long. That's right. This right. So this is what I get for this particular initial point. So it's clear. So the blue curve corresponds to the constant step size. The green corresponds to step size which is decaying as 1 over square root of t, and the orange curve is for step size 1 over t. Right? It's kind of expected. If you like, constant step size means that you're taking larger and larger steps. But let's maybe run this for more number of iterations, or suppose I just change this from 0.01 to 0.1, then what would happen? So I chose too large a step size. So with constant step size, the gradient descent just diverges. The other two converge. They converge slowly, but still they do converge because the step size is decreasing as t becomes larger and larger. So I have eventual convergence at a slightly slower rate, but it does converge. Now note that 0.01 is not the optimal step size. Right? So it's not easy to choose. The point that I'm trying to make is that it is not necessarily easy to choose the right step size. When we did the analysis, we said that if we choose the step size to be this particular function of L and D and everything else, then this is true. But if you're somehow able to find those parameters, L and D, well and good. That's great. You can find the optimal step size. But in many problems, L may be relatively easy to find. D is quite hard to find. You can maybe guess, but in general, it's a bit difficult. Sigma, again, may or may not be easy to find. Right. But if you are able to choose the right parameters, then that's great. Let me again go back to this particular choice of step sizes. Right, this is the performance. This is just using plain gradient descent. All right. Now let's try to implement the version of accelerated gradient descent that I have over here. Right, this particular variant of accelerated gradient descent. Let me have this to one side. Let me have this to another side, just so that I have a reference. Descent A B x naught XLS step size right. So I have this. Again, I choose an arbitrary x naught. In this case, I need to keep track of this y, yt, and yt minus 1. So I choose x to be equal to naught. I also need a y. I will initialize that also to be x naught. I need a y previous. So I initialize all of these to be the same. Now in accelerated gradient descent, I don't strictly have a step size. I have this parameter alpha, right? So alpha is something that is greater than 1. So I'll try to choose this in a heuristic fashion. And I'll choose alpha to be something like 1 over the step size. So let me use the same quantities. Take this. Choose. This is the optimal error. I choose the step size in this particular manner. Now I have to choose alpha. Or the square root of alpha will be, let me just choose this again, it's a heuristic choice, to be 1 over the step size, square root of 1 over the step size. Now I have y to be equal to x minus gradient f of x. I have to update x as 1 plus, let me compute this, beta to be square root of alpha minus 1 divided by square root of alpha plus 1 times y minus beta times the previous y. Okay. This is my x. I also have to update by previous, and I should also compute the loss, which is the function evaluated at the current x minus optimal error, and I'll just return the loss. Okay, any questions? Yeah.
I think people
Uh,
understand.
okay, so now I want to compare all of these algorithms in a single plot. So, this gradient descent. Accelerated gradient descent. Something went wrong. Okay, so these are the different, these are the trajectories of the loss for the different algorithms that we have. So on the one hand, we have these dot dashed lines which correspond to vanilla gradient descent. You can see that the objective is monotonically decreasing. That's promised by gradient descent, because at every step you know that the objective function will decrease. It's never going to increase. But on the other hand, if you look at accelerated gradient descent, it's kind of oscillating, not monotonically decreasing. But there is a trend, right? For example, if you take the accelerated gradient descent with a constant alpha, then it is upper bounded by something, right? You can upper bound it by, this trajectory is upper bounded by some curve that is decaying at a much faster rate than vanilla gradient descent. But the trajectory is not monotonically decreasing. That's something to be kept in mind. So in fact, let's do something more. Let's try to visualize the trajectory of gradient descent as well as accelerated gradient descent. Right, so let me try to do this. Let me take gradient descent. I will copy this function. Right, so I have the optimal error, I have the optimal XLS. Let me mark the optimal point. 0, XLS of 1. Okay, and at every step, I want to plot X. So let me do the following. Say run this for 100 iterations, and I choose a constant step size. This is kind of what the trajectory looks like, right? So this is gradient descent, and you can see maybe I should have also plotted the contour. Choose a slightly larger step size here, 0.02. So you can see, so this is the point, this is the optimal point over here, and this is the trajectory of gradient descent. Why am I not getting? Whatever. So this is what gradient descent looks like. This is the trajectory of gradient descent. But now let me also plot the trajectory of accelerated gradient descent. plotting this correctly. Yeah. In this case, accelerated gradient descent is in fact behaving quite nicely, I would say. But in general, it can behave a lot more weirdly. So let me just generate a new set A and B. And the same. And I'll again plot the trajectory of the two, right? The blue curve here corresponds to standard gradient descent, vanilla gradient descent. You see that at every stage it is trying to get closer and closer to the optimum. But if you see the trajectory of accelerated gradient descent, it was moving towards the trajectory in some sense, but it overshot, right? It overshot, but then again got close, again overshot, again got close, and so on. So it's essentially the trajectory is oscillating a lot. But notice the step size taken by the size of each step taken by accelerated gradient descent versus gradient descent. If you see in gradient descent, initially you take large steps, but then as you get closer, the value of the gradient becomes smaller and smaller. So the size of the step that you take becomes smaller and smaller. But on the other hand, in accelerated gradient descent, you're still taking very large steps, much larger than what you're taking using standard gradient descent.
Exactly how they go like around and then to the grade point. Why don't they just go directly?
That's the difference between so as I said, if you look at this particular quantity over here, right, you have this x of t minus some step size times the direction. At every stage, the direction is not exactly in the direction of negative gradient. There is additional term that is added that makes it go in a different direction compared to the direction of negative gradient. But you take a larger step in that particular direction initially.
This is for accelerated.
This is accelerated
Even
gradient.
the blue one.
Okay.
Even that one doesn't go in a straight line towards the grade point.
It doesn't, because that's the behavior of the objective function itself.
Can you plot the font?
Let me see if I can plot the contour.
Yeah, it is just perpendicular distance divided by
So what you could do, I mean, to understand it even better, what we could perhaps choose is a simpler problem. Maybe we just try to plot. Let's suppose that you just want to minimize norm of x square, right? We know that the solution is 0. X. Right? F. So this is just x. This is just n. Evaluate x, x. So, x0 sorry,
Instead of MP.18, yeah.
sure, doesn't matter. Uh, f q square plus p square do this
ALP.
a and b. Okay. This took a different step size. One. Yeah, it is overshooting, but you can't see how much it is overshooting in this case. So if I just don't plot this and don't plot this, it's a little harder to see, but basically it's taking very large steps initially. It overshoots, then sort of comes back, and then converges. So yeah, I should have thought of a slightly better example for this. But yeah, in the case of the least squares, if you maybe slightly modify the step sizes, then you'll see how it kind of overshoots, comes back, overshoots, comes back, and then but eventually it does converge, and it converges much faster than vanilla gradient descent. Right?
Because it's a convex function of phi anywhere but over.
I'm sorry, because it's a convex function.
Convex
Yeah.
will be input.
Yeah.
So it's fine even if it overshoots.
Not guaranteed, right? If you choose a very large step size, it will overshoot, then yes, you will definitely will not converge. So you have to be careful. But if you choose step sizes that are decaying with t, then you will kind of converge. But you'll converge at a much slower rate. Okay, so maybe let's stop here. I will continue in the next class.